problems, especially on this test, because AP is doing they're requiring less and less memorization of prediction of products. It's more about the application of it. So, but you still need to know how to use this sheet. So this sheet that I gave you for common oxidizing agents and reducing agents is important to have in front of you at all times when you're trying to predict products. So anything at the top of the list is usually a priority. Like, for example, oxygen is the best oxidizing agent, because that's kind of why it's called an oxidizing agent, because it's the presence of oxygen forcing the loss of electrons. So you want to make sure that you know how to use this. And basically, if it's at the top of the list, it's a priority on the common oxidizing agents, and if it's on the top of the list of the common reducing agents, it's a priority, meaning that it is very, very strong. It's going to force this reaction. So alkali metals are never in their solid state. They almost will always react because they're very likely to lose electrons. So why are they called why are they called reducing agents? They themselves are oxidized. They are incredibly likely to lose electrons. Specifically lithium. It's got one electron. It's just one of the highest on the reactivity series, and so forth. So speaking of the reactivity series, well, I'll show you in a second. It will cause replacement. It will cause single replacement to happen. So these that we went over briefly on Friday, I didn't go into detail on every single one because you guys can read, but you do know that all of these single replacement reactions are just simply based off the reactivity series. Metals replace, so free metals replace metals that are bound up in a compound if they're more active. Metals replace hydrogen from an acid if they're more active than hydrogen. But how would you know if they're more active? Say again? How do you know if they're more active? Activity series, thank you. So you're looking at, this is really kind of blurry, but you guys have your activity series kind of generally memorized in your head. Group 1, Group 2, Group 3, transition metals. The one that's kind of weird and it's kind of hard to see is that you have hydrogen ion right smack dab in the middle. Anything above it is more likely to oxidize. So they're really likely to undergo they're really likely to reduce something else. So they're more likely to be oxidized and lose electrons. Anything that's really low is going to be more likely to be reduced. So hydrogen's right in the middle. So we're going to use that as a comparison. And if you can kind of see, this is copper and copper. Copper is generally low in the activity series, like you kind of predetermined already from your basic knowledge of the activity series. So I'm going to use this occasionally today, but I want you guys to go ahead and start helping me answer these. Okay? So basically, we're going to write down the reactants, figure out if it's a simple synthesis, like Clayton was saying, you're like, how do I know when you do redox? Basically, you're always doing redox, but when you actually balance an acid or balance an base, it's dependent on if it says acid or base. So for this one, tell me the reactants. Reactants. Anybody? I need your help, people. Tell me spell it out for me. Cl2. Hep 7. It's added to water. And that's gaseous. Okay, so I'm going to force you to write your states because you guys can't write your states, which actually inhibit or limits you from actually getting your NIEs right, like on your Unit 2 test. So if you see gaseous, put gas there so you know you don't ionize it. If it's liquid water, it's pure liquid water. Don't ionize it. What does a non-metal oxide plus water make? Non-metal oxide plus water. Acid. What acid do you think it makes in this particular example? Nope, because there's no oxygens in hydrochloric acid. Chloric, or maybe perchloric. Okay, if you look at it and you're like chloric acid, that's HClO3. You've got 8 oxygens here. There's no way to really balance 8 oxygens and 3 oxygens. So if you go perchloric acid, then it's probably going to help out with your balancing act here. So what do I need to do to balance? 2 up here, and that balances out because you have 2 chlorines, 8 oxygens, and 2 hydrogens. Okay, is that the NIE?
Yeah.
Not quite. First part's good, right? ClO2, O7, gas plus liquid water. What's so strange about, or what's so important about the product? Why? Strong acid. So put 2 H pluses and 2 perchlorates. Okay? So this is kind of a good review of unit 2 as well. What's the question? What's the oxidation number of chlorine? You guys can see it. What's it say on your paper? And the reactant. So what's the oxidation state of chlorine? Go through your math in your head. Why 7? Tell me your process.
Oh, it's a -2.
O is a -2.
Times 7, you get 14 then.
So negative 14 on this side, you need a positive 14 on this side, so that's 2 times 7 is 14. All right, so oxidation stays +7. That's not hard, right? That is redox, though. That is, it happens to be a synthesis reaction, but it is redox. All right, you guys start the next one. I just need to get some stuff. There we go. So, gaseous methane is combusted. So what's methane?
C.
Okay, combusted. Reacts with oxygen. I'm doing basic review right now, okay? Make sure you're participating with me. Goes to
CO2.
and
Sure.
okay. And this does not specify limited oxygen, excess oxygen, or very limited oxygen, so assume it's normal amounts of oxygen. It creates full combusted products. Balance, I think you need a 2 on the water. And then, do we have anything that will ionize here?
No.
This is gas, this is gas, this is gas, and this is pure liquid water unless it's really, really a high number of high hydrocarbon, like maybe propane or butane and up. It makes such large amounts of heat it would vaporize the water, so you can put gaseous, but it's still, regardless, it's not going to ionize. What's the answer then to our question? What's the oxidizing agent? Or how would you figure it out? Oxidizing agents are the things. They're the ones that are reduced. Okay, so which one's gaining electrons? Which one? Oxygen's going from a 0 to a -2 and a -2. Right, in both of those oxygens it's a -2, so you're gaining electrons. Therefore, you're the oxidizing agent. And that makes sense because oxygen's a really, really good oxidizing agent. That's kind of the premise of it. Okay, acidic potassium permanganate. So potassium permanganate is added to what? What's it saying, y'all's?
Iron 2 sulfate.
Iron 2 sulfate. Okay, so that's kind of, this is what you're gleaning from the information. But it says acidified, or if it ever says acidified or acidic, that means it's in the presence of acid. So I like to just remind myself by putting in that above the arrow, because that means I know I'm going to balance an acid. So I'm doing this one as a review for your quiz. Okay. So before you can begin, you need to kind of isolate the things that are, are really strong oxidizing agents and really strong reducing agents, so you can predict their products. Potassium ion is going to be always soluble, right? Never involved. It's always a spectator. Sulfate can be, or it cannot be. So your choice is, first of all, permanganate, is at the top of which list? You have your sheet in front of you. It's a very common oxidizing agent, right? It's towards the top of the list. So that means it's going to force a reaction. So what does permanganate go to? Right now I'm running a half reaction. So permanganate goes to what? Mn2+ always. So if that's the oxidizing agent, that means it is what? Oxidized or reduced? Reduced. So the other thing that's happening has to be the thing that is oxidized or reduced. Oxidized. So your job is to figure out.
Bus 124 just arrived from campus. Please allow the students to your classroom.
So your job is to figure out, is it iron 2+ or sulfate that's undergoing the second half reaction, or that's involved in the second half reaction? What are your thoughts? This is iron 2, right? What can it go to? It could, iron 2 can either go down to iron solid or up in oxidation state to iron 3, right? Right? Okay. So this is being reduced. Then what could iron do? What does iron have to do? This is being reduced, so it's going from a +7 to 2. You said iron 2+ goes down to iron solid. This is what? That's also reduced, right? So it's got to go to iron 3+. So you kind of have to talk to yourself and go, okay, this one's oxidized, this one has to be reduced. How do I make it reduced? I make it actually gain electrons. This one's got to be oxidized, so this one actually is to lose electrons. So that's going to kind of help you out there, because the sulfate, that sulfate, the S is a 6+. To go down to sulfite would be a 5+. Yeah, 5+. So that actually would be gaining electrons as well. So you can actually cancel out that sulfate would be involved. So therefore it's a spectator. Do you see how the process of elimination works here? Okay, you've got to keep practicing by looking at your oxidation sheet. So here's your two half reactions. Let's go. What's next? And I'm for space now, so I'm going to make this big. Whoa. So what's next?
The balance.
How?
And oxygen.
Okay, add how many up here?
4.
4 waters. To balance out the oxygens, you add 4 waters, and then what? 8 H pluses on the side, and charge balance. I have a 2 plus on that side. I have a 7 plus on this side. 7 plus needs to go down to 2 plus.
5 electrons.
Add 5 electrons here. I'm sorry, I'm adding it up high. I didn't leave myself space. Right in the middle of your paper, okay? And then what? The iron example? Add 1 electron here. Okay, next. Okay, so you're multiplying this one by 5. Why? Right, so the reduction and the oxidized electrons must be equal, and then you just add it up. So 5 electrons you know is going to go away because you've actually done a good job of multiplying. So then H, 8 plus permanganate ion plus 5 iron 2 pluses yields 5 iron 3 pluses, a manganese 2 plus ion, and 4 waters. Alright, so that's how you balance an acid. If this question had said in a basic solution, 2 things would have been different. What would have been different? Yeah. Yeah.
So when you're writing the final answer, you just ignore the potassium and sulfate immediately.
This is actually an NIE. So the potassium ion and the sulfate ion are both both spectators, so we don't write them in NIE anyway. What if this was balancing base? What 2 things would be different? You have hydroxides down here, but would there be anything different about the half reactions? Look at your sheet. Is there anything different about balancing in base for either of these?
Yeah.
Right, permanganate goes to manganese dioxide, MnO2, in base. And that's just because on the sheet it says so. It's not something you're going to memorize right now, but you're going to kind of start to get the hang of how to read that. All right, what's the next example? You guys read it to me. I'll do one more right now.
Liquid octene is burned in air.
Liquid octene. What's octene? I didn't think that was the next one, but you guys might be right. CAH. How do you know that? Just like that. 2N. So octene and ene example is just 2N for your number of hydrogens. Burned in air, oxygen goes to CO2 and water. Okay, so that one's easy. I'm not gonna balance that one. It was number 6 or 7. Let's see here. No, skip 6. Go ahead and cross out 6. That's an exceptional rule. I'm not going to go over exceptions because they've changed the way they test on redox. Okay, number 7. 7 I'm doing because it's very similar to one you did in the lab, and I want to make sure you have a chance to fix that. So tell me your reactants. 7. So K2 CR207 plus
Sodium sulfate.
Okay, and what else is important in that problem? It what? Yeah, but it says something else in the problem, doesn't it? Acidified, okay? That means you're balancing an acid. Okay, so this is a weird one. Now, you did something similar to this with potassium permanganate and sodium sulfite, but first of all, pull out your 2 agents that are going to be reduced or oxidized. Tell me one of them. Or maybe tell me what your spectators are. Potassium's a spectator, sodium's a spectator. So what are the 2 things that are doing the redox?
Dichromate and sulfite.
So dichromate and sulfite. Now I'm going to write it like this for now, but I'm going to change the sulfite one in just a second. So dichromate and chromate, they both go to the same product. What is it? You should be looking at your sheet. Chromium 3 plus, good. All right, so let's balance that half reaction first. First step, add a 2. Okay, so you're balancing your non-H's and O's first, and then 7 14 H pluses. It's kind of like just you get the flow of it. And then, what's the total charge on the reactants? So plus 12, and then this side plus 6. So how do I get 12 down to 6? 6 electrons. Okay. Now the next one is said is an acidified solution. Sulfite can go to sulfate. Okay. But this acidified solution sometimes requires you, and it balances out really the same either way, but it sometimes requires you to actually allow for the hydrogen ion to react with the sulfite to make bisulfite. So I'm going to show you this way right now. Bisulfite. So this is bisulfite. It's just because in the presence of hydrogen, or hydrogen ion, sulfite likes to bond with the H+, and so it makes hydrogen sulfite. It's because it's a strong conjugate base. It's related back to acid-base chemistry. So let's balance it via this way. So what is your product you can make? Think sulfite. What are the two things that go together? Sulfite and sulfate. Just like nitrate and nitrite sometimes go together. Iron 2 and iron 3 go together. Copper 1 and copper 2 go together. Some of these things they're very similar to themselves. There's just an oxidation state change. So that's going to go to sulfate. All right. Next up. Okay. Not a hydrogen. A water, right? Add a water, and then 3 hydrogen ions. Okay. Next. So you see a total of a 1 minus here. You see a total of a 1 plus here. So then you get a 1 plus down to a 1 minus. You add 2 electrons. Balance by adding a multiplier of 3 here. And then 6 electrons go away. So dichromate plus 3 waters plus 3 bisulfites yields 2 chromium 3 pluses, 7 waters, 3 sulfates, and 6 H pluses. Okay? And then you would just cancel out some of your waters. So, 4. Yeah.
What about the H pluses on the counter?
Oh, I'm totally just didn't write those. Thank you. So 14 H pluses. And that cancels with, so that 14 H plus goes down to what? Did I forget something else? Oh, yeah. I'm sorry. So that's 9 and that's 14. So that brings us down to 6. 5. Sorry, I got up for early. I'm still not. I am awake. I did like an hour and a half of grad work this morning. Yeah.
So why do you only add 1 water to the
For this one?
Yeah.
Because this already this right here has 4 oxygens. This right here has 3 oxygens. So you add waters in order to balance out oxygens. So just to get this up to 4 O's on the reactant side. It just happens. You can't add oxide by itself. It doesn't exist. It actually exists in the form of water. So then you add, to counter your H pluses, you add your H pluses back on that side because it's an acid, and acids have 3 H pluses. Okay, so you guys get the point. You have to use your sheet to predict the products. Look at the rest of those and tell me which ones you feel like you cannot predict. Through 10. Eight. Okay, what are your 2? Tell me what one of the agents are. Agents is Fe3 plus, and what else? I minus. What does I minus have to go to? There's really no other choice. I2. What does iron have to go to? If iodine goes to iodine, what's happening? -1 to 0, so it's oxidized, so the other one has to be reduced. So what does iron 3 plus have to go to? This right here was what again? Okay, so you put your 2 electrons over here. So then this one. So what would it go to? Iron 2. And and you put your electron over here. Yeah, yeah? Okay, and then next, another one. 9 or 10? You feel like you can do those?
Okay.
Somebody tell me what permanganate has to go to. And number 9. Permanganate. Mn2 plus, like essentially always miscombinant acid. And then the hard part is the hydrochloric acid. Hydrochloric acid is weird because either H plus will go to H2 or Cl minus will go to Cl2. In this case, permanganate, which is being what, by the way? Is it being oxidized or reduced? Okay, so it's going from a 7 to a 2, so it's losing, no, it's being reduced. Right? It's gaining 5 electrons. So then this one's being reduced. Then what does the other one, which is the other case? This one or this one? What does what does H plus have to go to? H2. And chloride has to go to chlorine. So which of these satisfies the opposite? Technically, this one makes chlorine gas. Okay? You need to write that down. And then 10, magnesium solid plus nitric acid. What are your two, what is one of your half reactions for sure? Mg goes to Mg2 plus. I mean, there's no other way for it to go, right? It loses electrons, that's it. So that's the one that is oxidized. So the other one has to be reduced, and it gives you a hint in this one. It says one of the products goes to an oxidation state of 3 minus. Okay, so if you know nitrate, you've got H plus and you've got nitrate. Which of those could possibly go to maybe a product with an oxidation state of 3 minus? It says nitrogen must have a 3 minus. The one with nitrogen in it, right? Okay, so this is going to be just a spectator. So nitrate can go to something with a nitrogen of a 3 minus. So before we move on, tell me nitrogen's oxidation state here. Okay, so this is a -2, this is a +5. +5 goes all the way down to -3. Nitrite still has a positive oxidation state for nitrogen, right? That's a -2, that's because that's priority as oxygen. This would be a +3. So what's another form? NH4 plus, yes. Ammonia. This gets a +1, this gets a -3. Kind of have to play with the rules, right? You keep going through your priorities and go, which one does it satisfy? It goes to ammonium. I'm going to write that down. So those are your two kind of half reactions. I did not balance them, but I at least told you products, because the hardest part is really predicting the products. After you get them predicted, you just balance like normal. Okay? So if you need help on your lab sheet, then I'll ask for you to look at this first, and then come back and ask questions in your lab. Balance and acid base quiz now. Can we go ahead and do that? I'll give you guys a break in just a second. I predicted the products for you.
Oh,
You should not need anything other than a brain and a pencil.
Is there any definition?
No, it's just there's one. I'm gonna put definitions on there just for you. All right, guys, clear up your desk. Clear your desk.
Do I need
Yes, I'm sorry. You actually do need to take paper. These are the sizes of the quizzes.
oh my God.
They're little. It's because I got yelled at for coffee count. I don't like being yelled at for coffee count. I don't like being yelled at, period. Get a piece of paper out. Students are correct. I was checking. If you do not grab your books off the back last week, you grab your books, please. I just want to quickly talk about some of the common mistakes on this because it was kind of interesting. So I feel like this is one I definitely need to go over. If you didn't grab your books off the back last week, you grab your books. I think everybody has everything back now. I have an extra multiple choice. Did everybody get the multiple choice back? Talk to people. Okay. Multiple choice. Okay, so I'm just going to explain based off my thoughts on common misconceptions, but then this is something that you guys will come back and fix if you made below an 80. And I didn't even put the scores on here. Because to me, the score did not tell me enough information. It's actually what you got wrong. A lot of us did not study enough the reaction predictions for synthesis and decomposition. Okay, if that's you, that's not a whole lot I can do about that except for tell you non-metal oxides plus water make acids, metal oxides plus water make bases, chlorates decompose to what? Chlorates decompose to metal chlorides and oxygen. Some of those are just memorization, but they make sense. Like chlorates make oxygen because there's a lot of oxygen in it. Carbonates make carbon dioxide because they have carbon dioxide kind of embedded within it. So you've got to kind of commit those to memory. And you've got to make sure that you do not ionize gases, solids, insoluble salts. What are the only three things that ionize? Strong acids, strong bases, soluble salts, right? So things that are ionic that are in the solubility rules of soluble. Some of us just make big mistakes of like not seeing the fact that it said solid, it does not ionize, okay? So if it's silly stuff like that, that's something I just need you to fix up here. The things that were big problems. Look at the potassium iodide one, the tablet one, was I think question 9. That was an AP exam question from 2 years ago. This was something you were totally capable of, does not require you to know a whole lot other than lab practices, stoichiometry, and what the heck is percent mass, right? That's really all that mattered here. The big problem was that we did not balance, we did not put 2 iodide, plus lead 2 iodide, plus lead 2 yields lead 2 iodide. You just forgot a 2 there. That's not a big problem, but it's something you can fix. The one thing that they required on part AII was that you said spectator ions. If you just said these are what participate in the reaction, and you did not say this eliminates spectator ions, this ignores spectator ions, if you did not mention spectator ions, you did not get 0, you didn't get any points. So I graded strictly according to the rubric according to College Board. That you had to mention spectator ions. Part B, if you did not say something about making sure all the water is out, you didn't get the point there either. You'll notice that it says after drying, and this is a whole like precipitation reaction, just like what part of the lab in the alum lab? The sulfate part, right? You had to precipitate it out, you filtered it, and then you had to dry it. Some of us didn't dry it, but I made a point to say, hey, that's because you had too much water in it, and that kind of was hopefully feeding you this answer here. For part C, if you did not mention something about Ki being the, potassium iodide being the LR, the limiting reagent, because the other one was excess, because it said lead 2 nitrate was excess. That's really all you have to do. Some of you guys worked way too hard on that problem. You're saying at BDA tables, calculating molarity, you actually need to use your context clues, and it says excess, so that means the other one's LR. Cool? I'm just trying to give you tidbits. Those first couple should have taken less than 5 minutes. D, calculate the number of moles in the precipitate. What do you think you should have started with when it says from the precipitate in the experiment? You should actually, normally we start from LR, right? Normally you're like, oh, let me start with my potassium iodide and go find how much product can be made. But this problem, this whole question is regarding, we want to find determining the iodide content of the tablets. That means that this tablet is not a 100% Ki tablet. Can you read between the lines and see that they're saying that? Hopefully you're making notes here, because if you got to make corrections, these are good corrections to know. If it's telling you kind of up front, this is not a pure tablet, do not assume that LR is 100% Ki. So what you should have done is done mass difference between the filter paper and the last massing of 1.698 grams, and then gotten the mass of precipitate. What was that mass? Those of you who got that part.
236 grams.
So just the difference. So point what? 0.236 grams of PBI, 2. Then all you had to do was take it to mass. Take it from mass to moles. That was it on that question. But if you started with the wrong thing, that was a 2-point question, you got 0 points. Just because they do give partial credit sometimes, but not much. They don't give half points, they give whole points. The next part, E, you could have used part D to start part E to get the mass of I minus in the tablet. So if you took your 5.12 times 10 to the negative 4th moles, this question specifically said regard sig figs, like very carefully. I did not take off a lot for sig figs, but I will in the future. I want to make sure you're paying attention, because this question, if you got sig figs wrong, they would give you 0 credit on some of the parts of the question just because they're sticklers for sig figs. So there only should have been 3 sig figs in that question. Anyway, so take your lead 2 iodide to moles of I, so it's the internal ratio there, 2 to 1, and then take it to grams of I minus for the precipitate. And then that's actually your content of I minus, right? How do you get mass percent of the tablet? just divide it by the mass of the tablet, which is 0.425, which is given in the table. So you basically used almost everything in the table. Very, very important to have that data and use it. And then the last part, it should have been equal because nobody cares if you add more water. Molarity is an intensive property. That's just something that's kind of some background information. Molarity is not going to be based off, mass percent is a intensive property because it's not based off the volume present, it's based off the Ki tablet. And if you use the same amount, you have the same amount. Mass percent. Okay, next thing that was highly missed is the one with the V graph. Didn't I do a question like that in class? I literally pulled up that, I drew that on the board, and I said, oh, well, this is an excess here, and this is an excess here. And the bottom part is kind of like the equivalence point. Just like titrations are always between acids and bases, you can actually have titrations based on conductivity, or titrations based off percent ions. You can have titrations in many forms, and this was just another one. So the thing that I actually curved this test 6 points, plus whatever extra credit you got. So some of you guys got like 11 points of extra credit. So actually, I texted out if you got below an 80 on the test, you're gonna do test corrections. If your grades are inflated because I added and I curved. So I want everybody to correct things they got mistakenly wrong, despite your grade, because it doesn't matter. I curved it, so your grade is inflated, so you're welcome. But I want to make sure that you got what you need. So everybody's correcting something on this. We already corrected some of the multiple choice, so it's just mainly for response. On part AI and AII, you actually had to dissect the NIE and pull it into the two parts that made it up. So you notice, what are the two products of that reaction? Two products. Looking at your paper, guys. The V graph, what were the two products of that reaction?
Water and barium sulfate.
Water and barium sulfate. Water is a pure liquid. Is a pure liquid conductive? Mm-mm. Pure liquids are not ionizable. They are not conductive. Barium sulfate is a solid precipitate, not conductive. So what you should have realized is that there are two driving parts of this reaction. One was the making of a precipitate, one was the making of a pure liquid. So your reactions should have been for the neutralization reaction, which is the things that are neutralizing each other like acid and base to make pure water. And then the second reaction was, it literally said precipitation, right? So precipitation was the making of barium sulfate from its components, Ba2 plus and sulfate 2 minus. That was hard to see, but some of you guys kind of figured out this, I want this one and then I want this one, but we know that's, as a total, it is something that is of one huge NIE. But that's kind of what we were looking for there. And that was 2 points. So this is actually a question, this was in the 3 years ago. This is actually in the curriculum guide for AP Chemistry. This is one they really want us to know. Okay, so second big mistake was, part BII, when it says, on the basis of the equations, right, they're very deliberate. Equations, you wrote in part A. Explain why the conductivity decreases. So when they say equations, they literally want you to reference both. If you did not reference both, you did not get both points. It was, I gave 2 points. It's actually a 1 point question, but I gave you guys 2 points. So if you said something about pure liquid being non-conductive, you're good. If you said something about a solid precipitate being non-conductive, you were good. You had to mention both, though, because they said equations. They're very specific. The last one most people got was 0.12 molar barium hydroxide. And then 14 and 15, I'm not going to go over in depth, but I will say there was one mistake. That if you got down to the ion product, or the ions from the BDA table at the after part, that is it for your moles of that product. Okay, for this is, I'm sorry, not 14, this was number, what for you guys? 11 or something? 11, okay. Sorry, I had like 2 more FRQs in there and I took them out. So, if you're making product, that is exactly what you have. You do not refer back to the BCE for a ratio because you've already implemented the ratio in the BDA table. So if you implement the ratio in the BDA table, you've taken care of the coefficients used. Do not double use coefficients because then you're actually quintupling or sextupling or doubling or something the moles of something present. So your answers were off. So I took off minimal there, but that was a 7-point question. That was the only really big problem there. Some people just didn't get to it, which is fine. And then 15, I'm sorry, what is it, 12, the titration one, that was one where you just had to do stoichiometry to get to the product. So all you did was write your BCE and then do volume times molarity times the ratio of 1 to 1 over the total, over the volume of the acid. So at the end, when you did your 1 mole of acetic acid over 1 mole of sodium hydroxide, this there's stuff in front of this, of course. At the end, you just you invert the ratio, so you're dividing by volume of 10 milliliters. Okay, do not divide by total volume, it's just the acid, because they're asking specifically for acid concentration, not total shebang. And then the diagrams where you have to draw, before the reaction, what's free in solution? Before the equivalence point. I took multiple answers here. What are some things that are free in the solution before the equivalence point? Not before. Oh, I'll say minimally. Okay, I did give credit because it depended on when you said the equivalence point was. Okay, so you could have acetate ions. You have acetic acid present still. Okay, what if you've added a little bit of sodium hydroxide? What's present? Na plus. Any hydroxides present? No, because it's in limiting amount, so there's no free excess, or there's no excess hydroxides. After the equivalence point, what should be in excess? What should be present? Sorry. I heard sodium ion, because there's always sodium ions. They're spectators. They're still there. Hydroxide ions, because they're in excess now. What else? Mainly, what's not present after the equivalence point? What now is the LR and it's no longer present? The acid, the acetic acid, right? There should be no HC2H3O2, but there's totally just acetate ion free and present. And then some waters. He chose to draw waters. So we'll keep practicing that. But really, we just need I can adjust grades accordingly, but I want you to sit on that grade for a little while. So you guys keep your test until I get corrections back. Okay? I'm here all the time till B today, yeah. Yeah.
I'm missing half my text.
Still back there. What's yours? Okay, so I think we have time. We have 22 minutes. I'm going to do 3 examples of redox stoichiometry. Pull out your packet. Pull out your packet. This is the first example. It says lecture examples. It looks like this. On your packet, it's not this big, but it looks like that on your packet. If not, the questions on the board, I would like to do the first 3, and then you guys will do the last 5 for homework. The answers on the bottom. Okay? So tonight's homework, redox stoichiometry concept, which is 5 questions, and then read over the lab that is called potassium. It's got potassium permanganate reacting with hydrogen peroxide. It's an inquiry lab. We'll do the procedure in class tomorrow. I'm not going to have you guys do the procedure tonight. So I'm trying to get you guys sleeping, but I also need you guys to just respond. You guys have been totally way too quiet. Give me some fun day. I know, but I need some help. Okay. So write down, if you don't have it, write this reaction down. We're going to do the whole example. So if you don't know where it is, it's right next to what we were just working on in class, those 10 reactions. You are going to need a separate sheet of paper. God knows you can't write that small. Do not challenge that. It's not a challenge. Do not write that small. Some of you will try. Okay, so for a stoichiometry problem, what's always the first step? Doesn't matter what kind of stoichiometry problem it is. BCE. Okay, BCEs for these types of problems are just a little bit more complex because they're redox. That means we might have to balance an acid or base. So the BCE just simply takes longer to get to. After that, stoichiometry, people, it is the same. You will like this, you math people, because this is stuff we've done for a month now, okay? So what volume of this molar iron 2 sulfate is needed to completely reduce 50 mils of 0.4 molar sodium dichromate in an acidic solution? Wow, we know a lot of information, right? I just underlined it. You might want to write it out givens, but basically we have this. We have, so our question is what volume of that do we need? We have 50 mils of a 0.4 molar solution of sodium dichromate, and we know it's acidified. That's it. First step, we need to predict products. So what is very, very common as an oxidizing major? Which of these 4 things? Dichromate. You will see dichromate and permanganate come up all the time. You've got to know what they go to. What does dichromate go to? CR what? 3 plus. Then what? I'm going to go ahead and balance this half reaction. Whoa. 2. That's what a lot of people messed up on the quiz. If you were having a hard time on that second one, you just had to balance out your carbons first. Okay, so 2 there, and then you're like, okay, I still have 7 waters. Maybe. Invisible waters. Okay, then what? 14 H pluses. Keep going. We've done this like 3 times now, I think, today.
I know.
6 electrons. Okay. So keep going. So if we know that this is a spectator, this is our oxidizing agent. We need a reducing agent. Therefore, we need something to be oxidized. So what could be oxidized? Fe2 plus goes to what? Fe3 plus, losing 1 electron. Okay, that half-bit reaction is done. Next. Next. Multiply by 6. Okay, so basically our first step is balancing in acid. Okay, so then we get 6 electrons are canceled. Why do we need balancing the equation in a stoichiometry problem? Mole ratios. So Cr2O7 2 minus plus, let's make sure I do this right this time, 6 iron, 2 pluses, yields 2 chromium, 3 pluses, 6 iron, 3 pluses, 7 waters. The board is acting funny. All right, so we have, we're good here, right? Yeah, okay. Yeah, okay. Here's our BC. Now let's go back up to the top and you tell me where to start from here. Where do you guys want to start? With the sodium dichromate one, right? Because you know both the volume and the molarity, so what do? Get moles. Okay, so I like millimoles, but I'll use moles. So 0.050 liters times 0.400 moles of, and you like, I want you to write out this whole thing because sometimes their internal ratios matter, and if you don't start by writing out the whole thing, then you're going to mess up an internal ratio at some point in time in your life. 1 liter. That can life. Okay, so liters are gone. We have moles of sodium dichromate. This happens to be a 1-to-1 internal ratio. So this one you're pulling out just the part that's actually involved in the reaction, which is from 1 mole of sodium dichromate, there is 1 mole of dichromate ion. Okay, so I need to see the ion because that's what you're referring to in the BCE. Okay, so that's just simply pulling out internal ratio. Now, what's important? I don't care about chromate anymore, or dichromate. What's the question, people? So I'm looking for the iron, the volume iron 2 sulfate. So I need to get to iron 2. Yeah. Okay. So internal mole, or sorry, stoichiometry mole ratio, BC mole ratio. What is it? Dichromate to 6 moles of Fe2 plus. You would have never gotten that if you not balanced out first. So that's why this is important. Okay, so dichromate's gone. Now get me to what? Iron 2 sulfate. You gotta go back all the way to iron 2 sulfate because the question is regarding not iron 2, but liters of iron 2 sulfate. So that's why you have to go back. I know it's a 1-to-1, but deal with it. Iron 2, 1 mole of iron 2 sulfate, because sometimes we're going to have a problem where it's not a 1-to-1, so just practice makes perfect. Okay, and then, so iron 2 and iron 2 are gone. The molarity, how do I use the molarity to get to volume? Just flip it, right? Okay, so 0.200 moles of iron 2 sulfate per 1 liter of solution. Calculate in your head. You probably could actually on this one. Close to it. So that's like so this times point.
No.
0.2. 1, 2, 3, 20. That's kind of hard. I got you. The answer is 0.6. 0 liters.
You were saying 0.2.
No, I was just doing the first part. I wasn't even down all the way through. Okay, so 0.6, 0 because it is 3 sig figs all the way. Yeah. Okay.
Yeah.
So, and does this kind of make sense? You require, if you have, 50 mils versus 600 milliliters of something, when you require 6 times as much iron as that. I know the molarities are different, but it makes sense you have a whole lot more iron 2 sulfate used because you require 6 times as much iron 2 than dichromate. So it makes sense that it's a lot more. So reflect on it. Okay? Next one. This one tells you the products. Okay? Tells you the products. This is related back to mass percent though. Okay, so a sample of tin ore with a mass of 0.3 was dissolved in acid. Okay, so we know 8 plus. All the tin was changed to tin 2. So what's our first half reaction? SN goes to SN2 plus. As you read, a lot of things you need. What's next? Or what's not done with this one though? Where? On the product. Please write down these reactions. Come on. Okay, so all the tin was changed to tin 2. The solution was titrated with 0.05 molar potassium permanganate, and we required that much volume. So we know 8.08 milliliters of 0.050 molar KMNO4. All right, what automatically do you know about KMNO4? Immediately you're like, okay, permanganate is a really good oxidizing agent. It immediately goes to Mn2 plus in the presence of acid. Balance that quickly with me. You know how to do this. 4 waters and 8 H pluses. This is like, I've done this a million times now. And so there's a 2 plus on this side. There's a 7 plus on this side. 5 electrons. Don't forget that permanganate has a -1 charge. It does matter. 5 electrons. Okay? Keep going before we even finish reading the problem. Times 5 times 2. This should be like second nature to you at this point. So 5 tin solids plus 16 H pluses plus 2 permanganates yields 5 tin 2 pluses, 2 Mn 2 pluses, and 8 waters. Alright, so there's our BCE. Now, what is the question? Haven't even read the question. How many grams of tin were present in the original sample? So before we move there, tell me what's something we need to get in order to find A. So before we get to grams of tin, what unit have we probably already gotten to? Moles of tin, right? We can never go straight to grams. We always have to go through moles to get to grams. So really our question is, to get to grams, we need moles of tin. Well, how do we get to moles of tin? Probably using the BCE, but what did you know before that? What do you know a lot about? What reactant? The permanganate. So you probably know enough information to go ahead and get moles of permanganate, so you can get to moles of tin, so you get to grams of tin. Yes? Because this right here is 0.3 grams of an ore. It's like tin mixed with other stuff. So we're going to use that information to find the percentage of tin in the ore as well. Okay, so what are we starting with? I'm going to go millis this time just to give you practice. What am I starting with, guys? 8.08 milliliters of that permanganate solution, which was 0.05, right? 0.050 millimoles. This is me just giving you extra practice. Oh my gosh, MnO4 milliliter of solution. You don't change the numbers at all. You just put an extra M in front of the moles and the liters. Okay, so milliliters and milliliters of solution are gone. I'm in KMnO4. It's a internal ratio of 1 to 1. 1 millimole of KMnO4 contains 1 millimole of permanganate ion. please put your charges on your ions. That's the definition of ion. Next. So MnO4 to 10 solid. What's that ratio? So 5 millimoles of 10 solid, which is what this says, to 2 millimoles. It's just a mole ratio. Millimoles of MnO4, 1 minus. Okay. Can we just continue from here and get straight to grams? Yeah? You guys want to go to moles first?
Yes.
Normal
Yes.
moles? Okay. So, millimoles of permanganate go away. MnO4 go away. So we're in millimoles of 10. So a millimole is just, 1 mole is just 1,000 millimoles. So really we're just dividing by 1,000. So this is moles of 10, by the way. Last step. Molar mass. 10 is 118.7 grams per 1 mole. And do in your head. Good job, guys. 0.119887 grams. Why? I'm not, well, okay. The question, I know part A is an answer, and I would not record to that many sig figs in part A, but I need those many sig figs in part B so I don't have rounding error, correct? Part B asks for percent by mass. So what would you record this to for part A? How many sig figs?
3.
No.
2.
I think so too, right? Because this right here, this has 3 sig figs. This, 2 sig figs. So this needs to be recorded technically to what for part A? 0.12 grams of 10. Because that 119 rounds up to 1.2. Yeah.
And the problem is
Oh, is it? I don't have my problem in front of me. So then 3 sig figs. Was it 500?
Yeah.
Okay, sorry about that. So then, still, what's the final answer? 120. There you go. Okay, so then take this answer and then find the percent by mass. How? Percent by mass of the ore. You guys have the equation in front of you. Okay, so 0.119887 grams of 10 over 0.300 grams of 10 ore times 100, and that's like 39.96, but you would round that to 40.0%. Good. You guys can do the last one. You guys do the last one. I'll help you if I need to. It's number 3. It says peroxydisulfate. Okay. I will take your reaction from your lab tomorrow, so you guys have time to ask me questions. Okay? Because I didn't allow the time for questions today, so I'll let you guys turn that in. Thumbs up if you get your half reactions at least determined. Okay, thanks, Rob. Peroxidized sulfate has reduced to sulfate peroxide. That color. You guys get your BCE? You get your answer? No? Peroxidized sulfate has two sulfurs in it, so you should put a 2 of the sulfate immediately. And then also for the dichromate and chromium, you should have the 2 there. So that's the part people miss. So if you are one of those, just start by them, because that's going to be something you'll see on the test. I don't want you to mistake it, or actually you would probably immediately find your problem because you couldn't balance it correctly. So once you get your BCE and you read the problem again, and you're like, what the heck was asked? What do you want to start with? So 100 milliliters, or you're going to do 0.1 liters? Okay. So you're starting with the only numbers given to you, and those are regarding chromium-free nitrate. So if you start with that, 0.1, 0.000 liters, and times that by the molarity, 0.020 moles of chromium-3 nitrate per liter of solution. Where does that really get you? Yeah, okay, but tell me more. I want to know the next step. Okay, so internal ratio is 1 to 1 again. Okay, so really you don't care about chromium-3 nitrate, you care about chromium-3 plus, because that's what's in the BCE. So 1 mole of chromium-3 nitrate has 1 mole of chromium-3 plus in it. And then, because your question is that what's the mass of potassium peroxidized sulfate that's used? So before you get to mass of peroxidized sulfate, potassium peroxidized sulfate, you got to get to moles of potassium peroxidized sulfate. Go. What's next? Chromium-3 plus to peroxidized sulfate. So 2 moles of chromium-3 plus to 3 moles of peroxidized sulfate as 208, 2 minus. Okay, remember the question asked for mass of potassium peroxidized sulfate. So what's your next step? Internal mole ratio to get to potassium peroxidized sulfate. And this is where your internal ratio is different. So far, liters cancel, moles of chromium-3 nitrate cancel, moles of chromium-3 plus cancel. What changes here? What goes on top? Tell me first what goes on top.
Moles.
What's potassium peroxidized sulfate? Okay. And then what goes on bottom? Okay. So 2 minus, don't forget your charges, okay? If it were like magnesium peroxide disulfate or something like that, though, no, not magnesium. If it was like aluminum peroxide disulfate, you'd have a 3 on the outside of the peroxide disulfate, and nitrogenol ratio would not be a 1-to-1. Sorry, these are bad examples because they are all 1-to-1. And then last step, it gets to grams, right? So the question is step to get to grams. So 1 mole of potassium peroxide disulfate weighs 270.12 grams. So that's 0.810 grams based off 3 sig figs someplace. I might be lying to you. Let's see here. 2 sig figs. So, because you guys see this right here, there's 2 sig figs. So round that to what? 0.81. I'm not sure what it is here. Oh, perfect timing. Of the potassium peroxide disulfate. Okay. How different really was that from normal stoichiometry?
Not really, it's just
Just the BCE part, right? So this is why this unit's actually just an extension of Unit 2, because Unit 2 is all about reactions. These are all about reactions, but focusing on the redox type, and then stoichiometry again. What other thing did we do in Unit 2? In the lab specifically? Titration. You guys have another titration, but it's not from an acid-base perspective. It's from an oxidation state, aka color perspective. So the lab, find it for me. It's 4 to a page. It's called, oh gosh, it is called
redox
lab with hydrogen peroxide.
Yes.
Yes? Okay. You guys find it? It's called Inquiry Lab, Redox Inquiry with hydrogen peroxide in it. It's 4 to a page. I think it's the only other lab you have in front of you, so. Okay. So tonight, those last 5 on the problem set for the redox stoichiometry, and then read that lab, because tomorrow you're going to be getting in groups to do the inquiry procedure, so it's better if you don't waste your time reading if you already kind of know what's going on, so you guys have time to finish that procedure in class. Okay? Okay. I'll turn on announcements. Let me stop recording.